Welcome back, everyone. Good afternoon and good morning to Roland, and good evening to those in different time zones. And thank you very much, Roland, for giving this talk at 6 a.m. And Roland is a scientific software developer at the University of British Columbia. He is maintainer of the Einstein Toolkit. He is also my mentor. His research interest covers the gravitational waves and possible electromagnetic counterparts from comparable mass binaries such as binary neutron star and black hole neutron star mergers, and also extreme mass ratio binaries with supermassive black hole with a companion of white dwarf or stellar mass black hole. Today, we will be hearing an introduction to CarpetX from him. Only can get it from there. Yeah.
Okay, great. Thank you. So thanks for having me. Today I'll give a quick introduction on what CarpetX is. As you will see, these slides are largely based on previous presentations given by Eric Schnetter and Lorenzo Enogi. So every once in a while, you might recognize one of your slides. I thank you for having made them available and letting me use them. So with that having said, let's get started. So what's CarpetX? CarpetX is technically what's called a driver thorn in Cactus, which Steve may have mentioned in his introduction to the Einstein Toolkit yesterday. And as far as Cactus is concerned, the driver is just a special thorn, of which there can be exactly one active in the runtime, and you choose that one at start time with an active thorns line, just like you do for any of the other thorns. The driver is the only code, well, almost, that's actually dealing with parallelism. All the other thorns access parallelism via a defined API, either by the Flash or by the driver thorn. It has the responsibility of making the underlying parallel layer transparent to the application thorns, so that Cactus, you just say sync in your schedule statement and you don't know what goes on underneath the hood. This normally calls MPI these days, but I guess in the past there was different parallelization schemes that you could potentially use. In fact, there was a small project where people tried to use the different parallelization backends with the Einstein Toolkit. As far as examples of drivers go, there is basically three really that are kind of actually used, or were used at one point. The first one was PUG, the parallel unique form grid hierarchy. That was the original driver. It's Unigrid only, and it's part of Cactus. And that's actually the one that won the Gordon Bell Prize for the largest simulation at that time. The other one that's much more commonly used and much more popular is the Carpet driver developed by Eric Schnetter, I believe as part of his PhD project, actually, which offered mesh refinement using the Berger-Oliger mesh refinement scheme. And that's very convenient. This is what everybody uses, and people were basically waiting for this. There's also a basically unknown driver. As far as I know, Steve has written a small mini driver, mostly as an exercise to see what such a driver looks like. If you're ever interested, what does a driver actually do, and you don't want to look at the big ones, CarpetX, Steve's mini driver might be a thing to look at if you ask him nicely. And of course, the topic of today's talk, CarpetX, which is a new mesh refinement driver, which is built on a library called AMReX, which in turn is developed by the Department of Energy with their exascale computing project funding. So a driver in particular has to provide concrete implementations of parallelization, obviously, usually across nodes. That's MPI within a node. This used to be just OpenMP in Carpet, but with CarpetX, there's also CUDA and other GPU accelerator architectures. It is, or at least Thorns very tightly coupled to it, are responsible for input and output, both for analysis, that's data that you run to disk to then provide science output, as well as checkpoint and recovery, where you read and write your state so that it can continue once the wall time on your cluster has expired. It also usually handles coordinates in some way or the other. For example, in Carpet, this would be the Llama facilities that are tied to Carpet. Yeah, somewhat separate, but definitely supported by Carpet. And in CarpetX, this is the KPX functionality that Lucas has been working on. There's also reductions. Basically, you can compute the minimum, the maximum, the sum for norms, and all of these things that you would need during a simulation to ascertain that everything is working well. As well as interpolation of data to any arbitrary point, for example, to track black holes as they move across the system, or if you have particles that are either dragged along with the fluid as just tracers, or maybe it be the particles actually represent neutrinos and you're doing neutrino transport. So essentially, pretty much everything that the cactus flash promises has to be delivered by the driver. So really, I shouldn't have put a little cactus in there. This is all done by Carpet, the driver. All right, so let's take a little bit more of a detailed view on parallelization. So that's kind of a lower level view of what's going on. And Eric, who will be speaking after me, will go into the design decisions and internals of CarpetX. So in this case, a driver is responsible to allocate memory for grid functions. It handles memory, it's the one that allocates it. It's the one that actually runs the scheduled functions at the correct time. It's told by Cactus when they're supposed to run, but it's the one who actually makes the function call to them. It is responsible to distribute grid functions across multiple nodes, one way or the other, right? So you have a big chunk of memory that you claim this is my virtual grid function. You split that one into pieces. Here, 4 pieces, 0, 1, 2, and 3 across nodes. And then you send them out so that each node only handles a quarter, and you see that little dashed line here. This is what's called ghost zones, or basically halo zones, overlap zones that are required, such that all finite difference stencils find their neighboring points that they need to compute a finite difference also at the very edge of this domain patch here. CarpetX in particular, with the help of Cactus, will track which data on the grid is valid and which is invalid, and it will scream at you if you try to use data that is invalid, or if you claim that you provide some data and you don't in the end. It's very proactive about this. It has to do all the network communication to synchronize what's called these ghost zones, these overlap points, but also any data movement that goes on between different levels of mesh refinement or anything that involves the network at all. It implements adaptive mesh refinement. That means it has to move data between refinement levels, also across nodes, and it will have to track which levels require updates. Not every single level might need to update at every single time. For example, if you have subcycling in time, which is shown on the right here, in a figure that I've stolen from Liwei-Ji's talk a couple of days ago, then if you have what we call, say, no subcycling in time, and you might have multiple levels of refinement, the coarsest one, which is this thin line here, a medium one, this slightly thicker line, and then the highest resolution one in the middle. And if there's no subcycling in time, they all step with the same time step, which then is typically determined by the time step on the smallest level due to the Courant condition. On the other hand, if you allow these levels to step forward independently of each other, you are only required to take small time steps on the small level, while on the cursor level, you can take larger time steps. So you save yourself evaluation costs of the right-hand side because you're only doing the smallest one with the highest frequency, not all of them. And that's called subcycling. And the driver needs to at least be aware that it doesn't have to call anything on the cursor levels, for example, when it evaluates the functions at this time here. It also implements multi-block I/O systems. That's basically a different term for these different coordinates, what Llama and CarpetX provides. That basically means there's extra patches that it has to interpolate from each other, and of course it handles I/O, reading and writing grid variables. All right. If there's any questions, by the way, please interrupt me. All right. So this is kind of a generic driver. What specifically now does CarpetX offer to us? It offers true adaptive mesh refinement based on a local error estimate, which is a big improvement over what we typically used in Carpet. Carpet in principle can provide that, but it hasn't been used very often, and therefore it wasn't very well optimized for that. AMReX is CarpetX is optimized for this because it comes out of a community that does fluid dynamics. It offers very high order prolongation operators and also in principle restriction operators, similar order. It offers at the same time data that's stored at vertices of the grid as cell averages or as average over the faces. So basically, these would be something like the metric. This might be an average over the cell like a density. This might be a flux across a cell interface, or also some of the physics variables the magnetic field like to live there. Because of these different cell types, CarpetX is able to more easily support codes that have exact conservation of rest mass. You no longer have mass losses as you cross refinement levels or any of these things. And that makes for a much nicer code. So you can have a domain that's very much non-boxy, like the one on the bottom left, which is just a random grid setup that was generated, for a spherical, not sure if that was a neutron star or a boson star, but you can see it's not all squares anymore down here. The
Roland,
refinement
there is
levels.
a question in the chat.
Oh, yes.
Katie asks, how is the error estimate constructed for the refinement?
That's a very good question. Thanks, Katie. So right now, we mostly cheat, right? So most of the applications right now have been actually for binary black holes. And then we essentially reverse engineer that and basically put in by hand a cube, the way that the very nice paper on Gia Chombo found works best for black holes. But in principle, there's also people now working on basing mesh refinement criteria on the density and the density gradient, for example, and for scalar fields as well, where you, in principle, might have an idea where your, say, boson star is, but it is much more extended. So I think right now, this is mostly something where I'd say this is in principle possible. People are actually working their way through the GR Jumbo paper to check and see if all of these methods described in there work for us. Does this answer your question?
Yes, thanks, Roland. That's great.
Good. So you can see we're actively, of course, looking at what other codes have been doing. And GeoJumbo has been very nice because it's an open source code and it has been around for quite a while, using a lot of these features, and it's based on a somewhat similar library underneath of it. All right, we'll skip this picture that I stole from the AMReX docs because I'll come to that later. The other thing that AMReX offers to us is support for GPUs and much improved multi-threading on CPUs using tiles. So that means that parallelization on a node basically splits into two cases. If there are just CPUs around, then we have fine-grained parallelization on CPUs using tiles, which is what's shown on the left here. If I have a large piece of the grid that's handled by one processor, then it would be split into two tiles, the blue one here and the orange one here, that are more efficient to handle on the CPU, because going along this line and then continuing there might be able to use some of the data in the top left corner for the next row, and therefore have better cache usage than had I gone all the way across this thing. On the other hand, on a GPU, of which I might have only one single one, I don't want to do anything like that. I want to treat the whole thing as a large, gigantic vector and just have everything handled by the single GPU using its own threads, which really have nothing to do with CPU threads at all, and they're completely different beasts. There's also this correctness checking for the data, which is built in from the beginning, and in fact, it's enforced on you. You can't escape it. All right, so I've talked a little bit about this library called AMReX, which is used by CarpetX to handle all the grunt work. In some sense, all the heavy lifting is done by AMReX, although CarpetX is assuming more and more of the responsibility of AMReX to get more detailed control of what's going on. It was funded, at least at one point. Now the funding has changed a little bit, I assume, by the Department of Energy's exascale computing program, which has ended, and the funding has ended. AMReX supports what's called block-structured adaptive mesh refinement, which is in principle the same sort of Berger-Oehlinger type mesh refinement that Carpet support. So it should be a relatively easy transition for existing codes because it's not completely new. This is not, say, octant code or anything like that. It's designed to handle time-dependent partial differential equations for the most part, in particular fluid evolutions. They have a very nice picture here where they show all of these vortices of a fluid simulation, and you can see the very nice fine-grained mesh refinement that this code supports. On the right, this is just block structured. That means that while in principle you have these fine-grained things, logically what you store is still rectangles with a bit of a halo around it, and you split your domain into many rectangles on a fine level, which then overlaps, which is overlapped by the coarser level and overlapped again by an even coarser one. And these levels are nested like Matryoshka dolls. We never have a fine level here that sits directly on top of a coarsest level, for example. AMReX, just as a library, features use a very modern coding convention. It uses C++17. There is some legacy Fortran code in there, but I think it's getting less and less support for that. Parallelization-wise, it's always MPI across a network. So no Charm++, no HPX, just plain old MPI, like 95% of all the other codes. On a single node, it can be either OpenMP for multi-threads or NVIDIA, AMD, or Intel GPU support is built in. And it's transparent. In principle, you can write code that it works with any of these transparently. You don't have to do anything. There's explicit support for particles in there. It's no longer hacked in the way that we had it to some degree in in Carpet, which is nice if you ever think about doing neutrino transport with Monte Carlo scheme and lots of particles, or you want to do particle tracers, or whatever you want to do. So we can have millions of particles, hopefully very easily. They claim multiple load balancing strategies. I think so far we've used one. And it's still the case that you have to invest a little bit of human intelligence to make this thing perform well. Okay. And then finally, it actually has official documentation, which is great. At least the fact that there's documentation, the documentation itself sometimes is a little bit confusing, but it's there and it's infinitely better than having no documentation, which is what we had before. All right. So just as a picture gallery, this is a slide that I stole from Don Wilcox from many years ago when he presented on his code, AMReX. This is the targets that they have. So these are the codes, names of codes, WarpX, which is for accelerator design, so it's particle accelerators, down somewhere here. Combustion simulations, flames, over here. Flash is an astrophysics code, originally developed by the University of Chicago, if you might be familiar with. Multi-phase flow, so multiple fluids at the same time. AMReX, which is again a fluid code, but for low Mach numbers, so low velocity fluids. And then Castro, which is a type 1a supernova code. It's slightly different than some of the other supernova simulations that are done in Cactus, which might be type 2 supernova code. So if you saw Philip Möster's talk, this group is somewhat involved in those. All right, but this kind of looks similar to what we do, right? It's fluid dynamics. Everything is very non-structured, and it's large simulations. That looks exactly like what we want to do. All right, so then so far I've just said, okay, it uses GPUs, and I've made a big thing about it. So, well, why GPUs? And just in case you've been hiding underneath of a rock for the last 10 years or so, pretty much all the compute powers of the large computer systems, this is the Frontier system, which at the time Lorenzo Inogi produced a slide, was the fastest one. Now apparently it's El Capitan, but it'll look the same. It'll be racks of computers, and most of the compute power will come from GPUs. For these exascale systems, definitely. And if you look at them, this one here is based on AMD's, I think they're called MX1 GPU system. But you can see there's 4 GPUs in the system, and then there's 1 CPU with a bit of memory. So essentially, all that the CPU is doing, it's managing the GPUs, and it's not really contributing much to compute power. So you have to use them if you want to use any of these bigger machines. It's much harder now to get any computer time that don't rely on GPUs than otherwise. They're also fiendishly expensive. You want to make good use of them because they cost as much as, well, as much as a good car. Right. So on the other hand, why do I have to use GPUs? These things are annoying. GPUs are not just an alternative to CPUs, right? They are not just plug it in and it works. I mean, it'll work, but it'll be really slow. It's going to be heterogeneous computing where you have different setups. You've got the controller, which is the CPU here, which has lots of cache and a bit of DRAM, and it's really designed to do cache-based workflows where everything is a little bit different, but it's not all the same all the time. While GPUs have much more investment into compute resources and basically very little cache. And then they're designed to do the same thing all over the time with many parallel threads is what they call this thing. So the accelerator is really for parallel tasks. They were originally designed for graphics rendering. We do the same thing for every single pixel. And yeah, they are designed for parallel throughput rather than low latency access. So they really hide memory latency from you by just having many things trying to access memory at the same time. There's a bit of a graphics overview what this looks like, stolen from NVIDIA themselves. All right, so why go to this? Why not just build faster CPUs? They're so much easier to use, much simpler model. Just give me a GPU that runs at 100 gigahertz and I'll be very happy. And if I could get one of these, I would be very happy. Turns out you can't. And that has been true for a long time since. So the next couple slides are mostly showing you how CPUs have evolved. This is a plot that shows you the clock frequency in megahertz of GPUs over time, starting from the 1970s, from the first couple CPUs. And you can see, this is a log plot, until maybe the early 2000s or so, this thing was nicely growing exponentially. So everything was getting faster. If your computer was too slow, just wait a year and it'll be twice as fast. and that was great. And since then, this hasn't happened anymore. The megahertz numbers have basically stayed the same, and roughly megahertz numbers are an idea of how quickly can you execute instructions, how quickly can you act on a new situation, the latency essentially. And that hasn't changed. And the reason why this hasn't changed is that it's too expensive to make these things faster heat-wise. You can't get the heat out of the system. These things are hotter than the hot plate on your stove, so they would just melt. And at the same time, you can also see that if you look at performance over time, again, slightly different range of DRAM memory basically and CPUs, you can see that the CPUs ran away. They are much, much faster now compared to memory than they were in the 80s. So now you can't just make these GPUs ever faster because it doesn't help. They can't get the data in fast enough. All right, so that means the way to solve this one is what's shown in this picture on the left, where in particular, I would like you to take a look at these black dots. This is just numbers on the right and time on the numbers on the left and time at the bottom. And you can see that at the beginning of time, we had one logical core per CPU socket, and that was good until about the mid-2000s, when the CPUs no longer got fast as megahertz-wise, and then you have more and more cores going in there, and that's just for CPUs, and now you're sitting at maybe 100 or so per CPU socket, and of course these GPUs are the extreme of that. They have thousands of cores, each one fairly slow. But with these slower cores, you can actually get more computer time out of it, because if you make the core, say, half as fast, you can pack more than twice as many of those into the same chip without melting the chip. That's why we want to go that way. We don't want to make the frequencies ever higher, because that increases the heat. Keep the frequency fixed, but you put in more and more cores so that the product of frequency times number of cores still goes up. That means compute power still goes up over time, just the number of frequency or the single thread performance doesn't go up in the same manner. All right, and then the last one here, that's kind of the cautionary slide that's called Amdahl's law, that shows you what speed up you can get, assuming you use a certain number of compute items, be that processors, graphics cards, humans with a calculator, whatever else, if you can make certain fractions of your code perform in parallel. You can only make half of it perform in parallel, no matter how much resources you throw at this thing. It's never going to get faster than twice as fast than originally, because the serial section still persists. You can make it 95% parallelized. You can make it 20 times faster, maybe use 20 parallel resources efficiently. So that means that for science code, you have to make 99.999 something or the other % of your code parallel to really go to a factor of 1,000 or so speed up. All right. So this was the goal. To get there, we'll have to write code that uses CarpetX efficiently, and that's kind of a sneak preview. For those of you who are just starting, this will not tell you much. For those of you who have used Cactus code, this is the future. So you will have changes in the way that how you have to write your code. You'll have to be more explicit in telling the system what you're doing. You have to tell it now what you're reading, what you're writing, and what needs to be exchanged over the network. The last one was always true. The first two were not. Your code will be C++ code almost certainly. There is some Fortran support, but not so much. Going to be C++ because this is forced on us by AMReX. And it will look somewhat different. It will be much more explicit in telling the system what you want to achieve rather than telling the system what to do. But in the end, it's still somewhat recognizable science code. Somewhere here happens that this is actually something that claims to compute an error measure for the regrid. Although I think this is just made up, but it shows you a bit what your code would look like. It still is recognizable code, but it's much more modern functionality. It uses lambdas in here. You can see these auto things in there. It's template-based, so it's a little bit more complicated to write this code maybe than your simple 3D Fortran loop. All right. So I'm a little bit slower than planned. We'll see. So let's see. So CarpetX is new. What are the changes that it actually introduced by CarpetX? So let's see. On the left-hand side, kind of, okay, CarpetX is still using Cactus. So the basic concepts that you're familiar with if you've used Cactus before stay the same. There's still grid functions, grid arrays, grid variables. All of this exists. There's still ghost zones, although they are a little bit differently maybe before. You still use parameter files to control what's going on at runtime, and Cactus computational language files to control things at compile time. So that's your perm CCL, interface CCL, and schedule.ccl. So these all exist. They just have a little bit different information in there. Some things, on the other hand, change, maybe drastically. Some change out of necessity, because just some things are not supported by AMReX, so there's no way they need to change. Some things change to improve correctness, because we are doing this for the second time. So this, of course, is our chance of getting it right. And you might read this a little bit ironically, because clearly there is a bit of a second system effect in there, but it should be better than before. We've learned in the last 20 years. And some things change just out of convenience, because, well, somebody has to implement this, and it pays to make it easy for the implementers. So things change, but hopefully not too much. I may point out this is not actually any different from what happened when there was a transition from Pug, the Unigrid driver, to Carpet. There's a benefit that drove people to use Carpet, even though there was a cost transitioning. The same is true here. All right, so what changed? Subcycling in time in CarpetX is handled differently than in Carpet. That isn't so much a CarpetX thing, but we found we want better ways, and these better ways are different from what we had before. At least we hope they are better. This is LibG's work. We have a new time integrator, Thorn, called ODE solvers, which is much more tightly coupled to CarpetX, which is nice because, in fact, the driver and the time integrator have to talk to each other a little bit to make this thing efficient. Boundary conditions are now handled implicitly. So you no longer tell it so much, apply the boundary now, but you register at one point, this is the boundary that I want. I want this thing to be reflection symmetry. I want this to be an outgoing wave symmetry. And then the system handles applying the boundary condition when required. Multi-threading is very different. It's much more efficient on CPUs, but it also means looping is different. So that's the biggest change that people will notice. You no longer have OpenMP pragmas all over in your code. It's done by the system for you, but it means your code now has to be thread safe. You can use GPUs. That's the big selling point. And because this is a completely different architecture, there is some changes necessary all over the place. But if you do it right, you can actually write code that works on GPUs and on CPUs from the same code base, which is a big benefit for debugging and for production. CarpetX now offers true self-centering concurrently with vertex centering. So you now can have a situation where you actually have a metric that's stored at the corners of your cell where it wants to live, it wants to be sampled there, while the fluid quantities are defined as averages over the cell, and therefore in some sense defined at the center of the cell. And the cell edges, the faces actually align so that when material flows from the coarse to the fine level, this actually happens at the same place, and you can account properly for what goes left and right and correct for that if you want to. There's different I/O file formats that are being used. Carpet used a homegrown file format, which works. It's very easy to write, but it's not really well optimized for reading, so people have trouble visualizing that occasionally. Here, we try to use file formats that are defined by other people and used by other people, such as the Silo file format for visualization, and right now OpenPMD for checkpointing and recovery, or maybe in the future a format called Conduit, that hopefully are all more efficient or better supported at least. All right. Let me see. So, okay, so I'll go a little bit of fast review what's different. So where do you see changes? Cell-centered versus vertex-centered variables. So there's two different variables now. Vertex-centered on the left, you can see these corners all align. Data is defined at the corners. This is exactly what we had in Carpet before, and that's fine. We could also have cell-centered things. These are the circles and the squares here. Ignore the colors for now. And you can see these are defined over a cell. Here they call that the center, but really this is cell average. So it's just the cell has a quantity rather at the corner. But you can see that these faces align. It could also be that it's partially, for example, something's defined on the faces. Then it's cell-centered in this direction. Basically, it's centered on the face, but it sits exactly at that face in this direction. So it's vertex-centered here, cell-centered there. So it's mixed. And then you can have edges, which I can't draw because I need a third dimension. And that's all you can have. You can have 6 faces, no, 3 faces, 3 edges, vertices and cells, and these are 8 combinations, and that's all you can have if you have 3 dimensions, and each dimension has cell or vertex centered. Right. This gets reflected in interface.ccl, where a typical line would have before looked type of variable, name of variable, data type of variable, name of variable. This is a grid function rather than a grid array, and then maybe a name. Now you add an extra tag called centering, which can be any combinations of the letters C and V, cell-centered, or vertex-centered, or This one here, that's a face-centered one, and that's an edge-centered one for the vector potential, for example. And that's a fairly benign change. Add this one so the cactus knows what you're dealing with, and Carpet learns from cactus. This is new syntax interface.ccl. There is no support yet, unfortunately, for different centering for individual group members. So you right now would have 3 separate variables for the 3 components of the vector potential, and similar for fluxes, which can be inconvenient for some applications of mesh refinement. We do support at this point real integer and complex data types for grid scalars and grid arrays, but not for grid functions, the stuff that actually lives on the 3D grid, for which only CCTK real is supported. That's a restriction of AMReX. We can do very little about that. Okay. The big thing that's new that will actually probably trip you up, but it's a good thing, is CarpetX implements data validity tracking. This comes from the fact that writing a correct schedule for Carpet is very difficult. People get it wrong all the time, and it's not completely wrong, it's just slightly wrong. So the answers are somewhat off, but probably good enough for publications, but maybe not. So errors in the schedule are a major source of bugs in Carpet for science codes, and hopefully not so much for Carpet itself. Many bugs remain undetected just because the effect is subtle. And this can result in using uninitialized variables, using outdated variables, or recalculating values too often, more often than you would need. This might go well for 10 years, and then it fails, and then you hit your head against the wall because this darn thing fails, and you don't know where. It only ever happens in production on 1,000 nodes, and you wait for 2 days for anything to happen. So you really, really don't want this to happen. CarpetX tries to do it better. It tries to keep track of the validity of information for the interior and for the ghost regions separately, for all grid variables, during time cycling, during adaptive mesh refinement operations, and after checkpoint recovery. It also forces you, as the science driver, to do the same. You have to tell it, what are you doing? What are you reading? What are you writing? Where are you reading it from? Where are you writing it to? This is supported by the presync infrastructure that Steve Brandt added to the Einstein Toolkit a while ago. If anything fails, CarpetX also tries to tell you why, in particular, something is invalid. It tells you who said this is now invalid, so you can track back and see why this is happening. On just the parameter file level, it does require that you set presync mode as error. I hope I got the right keyword there. Otherwise, it tells you do this. I won't run otherwise. All right. This requires changes to schedule.ccl. Again, a typical example. Schedule statement. This is from the AMReX hydrodynamics code of Jay Kalinani. And you have to declare what you're reading. This one says, I'm reading in the metric. I want the metric to be defined everywhere. I'll read it in everywhere. Maybe I take derivatives. I will read in the rest mass density, but only in the interior. So it's fine if it's still defined in the mesh refinement boundary, in the physical boundary, in the reflection boundary. I just need it in the inside where I have enough ghost zones left and right, even though I promise not to use the ghost zones. I'm going to write only into the interior, not into the ghost zones. I'm also not reading the density anywhere. It also tracks grid scalars and grid arrays, which can trip people up because these were often just treated as global variables. Nobody cared about them. Now we care. Carpet is very proactive about this. If you claim to only ever write to anything, like here, it'll make sure that when it calls you, whatever is in there has no data. No data here means there's a none. It'll fail if you read these. It'll check, are there any nons after you've written things out? If there are any, it claims you haven't written there, don't do this, it'll fail. Similar to reads, if somebody says he's going to read a variable, it checks that this variable doesn't contain none, otherwise it fails. If you only ever read from a variable, it'll check that you actually do so. It'll checksum the variable before, and it checksums it afterwards. If you've changed it, it'll complain, at least in debug mode. This poisoning, as said, can be turned off, production runs, but the intent checking, the reads and writes, persist. You have to have them in there. All right, so big warning, you should not work around the system. I'm sure you can. Don't, or else. So really, please keep this. This is for the code's benefit. It makes your code better, even though it can be a pain in the backside. All right, so in my last 10 minutes, we'll skip some, I guess. Although this is my last couple of late slides, so changed on the source code level. So we change how data is accessed. Underneath the hood, everything is still a flat 1D array. Nothing has changed. But we now support vertex cells on the face and not variables. It can be on a GPU and a CPU. It could be tiled on a CPU, but not on a GPU. but there's also very limited Fortran support. So we need to change things a bit. We use a new macro to declare things, declare CDK arguments X, and then the name of your function. That's kind of inherited from the precinct infrastructure where there was no X, now there is an X. This means that then the grid variable that you see in your source code, for example, row, is no longer a plain C pointer, but C++ object. Also, only variables that you declare in scale.ccl are accessible. That comes from precinct. And your scheduled functions are now being called in a multi-threaded manner. That means all static variables that you've ever had in your scheduled functions, for example, you cache something because you only need it once, you read an initial data, you do a pre-computation, all of this needs to be protected against multi-threading with an OpenMP critical section. All right, second change to the source code, not only has access data changed, but also how you loop over grid points has changed. These loops must know how centered the data that you want to access is. So that means you can't just have a single loop, you need separate sorts of loops depending on how the centering works. This is because there's one extra data point or data value for vertex center directions. That's basically a fence post fence problem. There's one more fence post, then you have fence elements. And that's the same thing. The vertices are the fence posts, the fences are the self-centered stuff. And you must take tiling into account if you're doing this on a CPU, because the tiles, these different colored blocks, blue, orange, green, and red, as you can see, there is no explicit overlap because you're in the same memory region. You can just access your neighboring tile, and that's great in here for ghost zones. But if you set the edge, then of course there is no neighboring tile. You actually have to reach out the network to your neighboring processor. So the tiles are not all equal. There's an inter-tile boundary and an intra-processor boundary, I guess. No, inter-processor boundary. So we borrow some context from AMReX to handle this. There is a looping construct, loop and
Well, I see other people move, so I think it's not my internet connection.
Yes, there's a problem with Roland's connection. Thank you, Rick.
Let me quickly continue. So I guess the loops are different. You need to take into account how centering works. Also, the boundaries of the loops are different because they need to take tiling into account, because these tiles have no ghost zones among themselves from blue to orange, orange to green, but there is between processors, obviously. So we borrow a little bit from AMReX with these things, and this is what the code looks like. Here we go. So again, in red, you can see actually most of this has changed, but I'm just highlighting the pieces that are actually very changed. So let me just show you this, and you'll see this. There's a wave equation or a heat equation X example that we go through later on in the seminar. So this should be fine. All right, I'll skip this one in interest of time, and I'll just show you the CarpetX contributors. This is a picture that was taken at a workshop at RIT a couple of years ago. This is the main author. This is the official picture on the homepage. And this is Swapnil Shankar, who's a student at the University of Hamburg right now, who contributed a lot to the initial development, in particular for the mesh refinement infrastructure in there. But he's not here because he sits in Europe. This was done in the United States. And that's it. Thank you very much.
Thank you very much for a very nice introduction, Roland.